Alright, what's up guys? In this video we're going to pick up with some vector calculus here. We're going to be talking about Stoke's theorem. So here it says a circle C in the plane x plus y plus z is equal to 4, has a radius of 3 and a center 3 comma negative 1 comma 2. They basically want us to use Stoke's theorem here to evaluate the line integral, basically where C has a counterclockwise orientation when viewed from above. So the first thing I'm going to do is write down Stoke's theorem and just kind of give a general explanation for it, and we'll get started with the problem. So let's just go ahead and get Stoke's theorem out of the way. So Stoke's theorem is just a higher dimensional version of Green's theorem, and what it does is it allows us to relate line integrals to surface integrals. Okay, so this is Stoke's theorem. It's going to be f dot dr, and remember on this left hand side over here, this is our line integral, and then on the right hand side over here, and when I say right hand side, I'm referring to the side behind the equal sign. This is our surface integral, of course, and you can always tell the difference between a surface integral and a double integral by looking at the differential. In the case of the surface integral, we'll have the differential ds. With the double integral, we'll have the differential dA. Okay. So again, let me just quickly remind you guys of what our n here is. So remember, that's just the unit normal vector to our surface S. So this is going to be our unit normal vector. We can just say to S instead of writing down surface. And this notation here that you're seeing, keep in mind that this is just a three-dimensional curl. Now, about time you get to actually learning about Stoke's theorem and actually using the theorem, you will be familiar, or should be familiar, with a lot of what you see in the theorem itself. So when you actually get here, this may look a little daunting right now if you haven't gotten to vector calculus yet, but by the time you get here, you will have seen all this stuff, and none of this stuff will be foreign to you when you actually get to it. Okay. Also, keep in mind, and I love to do this, is because I think it's very important. A lot of times in math, theorems, formulas, and stuff like that can be written different ways, and they actually mean the same thing. So if someone writes Stoke's theorem this way, know that it's the same thing. It's just written a little differently. So we got our surface integral, and they may just write it curl f dot n ds, and that dot n ds there, that's the dot product. And remember how we get the three-dimensional curl is we take the cross product of the del operator and f. That's basically how we do it. Okay. So the first thing we need to do is calculate the curl. So all we have to do up here is we need to just go ahead and look at our given vector field here, and we'll calculate the curl. So what you do for that is you set up the matrix, because you're just using cross products to do it. So remember, our first row is ij and k, those unit vectors. The second row will be the partial with respect to x, the partial with respect to y, and the partial with respect to z. And then we'll take the components of our vector field, which are 0, 2z, and negative y, and we will go ahead and calculate the curl here, which again is just going to be our cross product. Okay. Now the reason why it's the three-dimensional curl, now remember, you can calculate the two-dimensional curl as well, obviously. So if you've seen the two-dimensional curl, that's a little bit different. But this is the three-dimensional curl, and again, we're just going to use our cross products here. All right. Get another sheet here so we can pick up with our little cross product. And the better you get at the cross product, the less steps you have to write down. But for the purposes of the video, I'm going to write everything down. Okay. All right, so this is what we got now. So we'll break this up. And what we'll have is the partial with respect to y, the partial with respect to z, and we'll have 2z minus y, because I'm going to eliminate the row and column containing the first unit vector, which in this case is I. And again, once you get into this point, you will have seen cross product quite a bit, so this won't be hard to you at all. Now we continue, and then this time this will be the partial with respect to x, this will be the partial with respect to z, and then this will be 0 and minus y. We put our j on the outside, and we'll fit our last one in here, and we'll tackle on our k on the back end. And so for this last one here, we got the partial with respect to x, the partial with respect to y, and then we'll just simply have a 0 and 2z, and our unit vector k goes on the outside here. Let's go ahead and calculate our curl. And it's a pretty straightforward process. Okay, so remember, when we're cross multiplying here and then subtracting, we're also taking partial derivatives. So make sure that you're doing that. So in this case, it looks like we're going to get minus 1. If I take the partial with respect to z for 2z, I get 2. So that's going to be 1 minus 2. We'll tackle our I on the outside there. Then we got the partial with respect to x for minus y, which is obviously 0 because we're taking the partial with respect to x in that case. And remember, when you're taking the partial derivatives with respect to, like for example, if I'm taking the partial with respect to x, we're treating all other variables as constants. So this would just be 0 minus 0. And if you notice, over on this side, we also get a 0 minus 0. Because the partial with respect to x for 2z, well, that's 0, because we're taking the partial with respect to x. And the partial with respect to y for 0, 0 is a constant, is 0. And so after doing all that, we can easily tell what our curl, our three-dimensional curl here is going to be. So our three-dimensional curl here is going to be minus 3i. So that takes care of our curl. And that's one obstacle out of the way. Now let's deal with our unit normal vector. So our unit normal vector n, okay, remember that's just n over the magnitude of n. Now remember, n is just going to be equal to del x plus y plus z minus 4. Because if you go back here, notice that we were given the circle C in the plane x plus y plus z is equal to 4. So basically all I did was I went ahead and subtracted 4. And so that's what n is going to be. And so essentially what we're going to have is 1 comma 1 comma 1. And remember that the magnitude of n is just the square root of the sum of the components squared. And that's just going to be 1 squared plus another 1 squared plus another 1 squared, which we know is the square root of 3. Now, if you're wondering where the 1, 1, 1 came from, I took the partial derivatives. Okay. So now we got our unit normal vector. And it's going to be 1 comma 1 comma 1 all over the magnitude, which was the square root of 3. And if you want to, you can just write that as 1 over the square root of 3, comma 1 over the square root of 3, comma 1 over the square root of 3. Now, typically, it is not really proper, I guess, math technique, so to speak, to leave square roots in the denominator. But we'll leave it alone, and you'll see the benefit of it in just a minute. So now we basically have everything we need to go ahead and deal with the integral itself. So we got our line integral, f dot dr, and that's going to be equal to our surface integral, Now remember what our curl was. Our curl was minus 3i. Now we'll take the dot product of that with the unit normal vector, which in this case was 1, 1, 1, all divided by the square root of 3, and then ds. Okay. All right. So what we're going to get is I'm going to pull out a negative 3. I'm also going to pull out I'm sorry, not a negative 3. I'm going to pull out negative square root of 3, excuse me. And basically what that leaves us with is the integral of ds, because that would just leave us with essentially 1 on the inside. Well, 1 times ds is just ds, so you don't really have to write 1 ds. And so this is essentially where we would end up. Now remember, it says that a circle C is in this plane and has a radius of 3 and a center 3, negative 1, 2. Now remember that the area of a circle formula for that, let's just remember that, right? So remember the formula for area of a circle is A is equal to pi r squared. Okay. So essentially what we got is negative square root of 3 multiplied by pi. Now remember what r is. R is 3 because it says it has a radius of 3. So r is 3. So we stick 3 in. So we'll simply get 3 squared, which we know will essentially just give us negative 9 times the square root of 3 multiplied by pi. And that would be our answer. So let me get another sheet. So for our final answer here, when we use Stoke's theorem to evaluate our line integral, looks like we get negative 9 times the square root of 3 multiplied by pi. That's given we use Stoke's theorem, of course. And that would be our answer. So the only thing, like I said, that we really, sorry guys, I have to circle it here. I have to do that, so let me do that right quick. So the only thing we really did here was just calculate the curl. We already knew what this n hat means. Again, that's just your unit vector that's normal to our surface. And again, all we had to do is just basically run through the criteria that we needed to run through as it pertains to the theorem itself, which is calculating the curl and doing our dot product and so on and so forth. And we were able to arrive at our answer. And that's how you do it. So let me know if you got any questions about it further. We can talk about it. I'll see you next time.